In this lecture, we want to take a look at some faster sorting algorithms. In the last lecture, we looked at three algorithms that are n-squared in the average and worst cases. We want now to look at some algorithms that provide better performance than this. So therefore, we want to consider this time merge sort, quick sort, shell sort, and radix sort. The complexity of all of these algorithms is better than n-squared, with the exception that in the worst case, quicksort is big O of n-squared. We want to avoid that worst case, of course. Other than that scenario, all of these algorithms are better than n-squared. Merge sort and quicksort are n log n. The shell sort algorithm is an interesting twist on insertion sort. It is difficult to analyze, and so we have really no complete analysis done on shell sort. Rather than that, we have an estimate of the complexity of the algorithm. Radix sort is a special purpose algorithm that in fact is linear. That is better than any other sort algorithm. And linear is as good as it could possibly be, because if you're going to sort n things, then you can't do it in less than n times. So big O of n is the absolute optimum result you can ever have. However, it has a great deal of overhead, which makes it slower than the other algorithms, which are actually slower by comparison. That is, if you time radix sort with quicksort will be faster based on wall clock or observed times. However, the complexity analysis shows that radix sort is in fact the faster algorithm, even though it appears not to perform that way. If we were able to create very, very large arrays in memory, eventually radix sort would win out over quicksort, but we're not able to make large enough arrays in memory at this time. So let's take a look at the first one, the merge sort algorithm. This algorithm is remarkably consistent in every case. The initial ordering of the array is not terribly important. The performance of the algorithm will be consistent no matter how the array is ordered. It is stable, which means it preserves the ordering of duplicate keys, but it is not in place. It's not in place because we're going to have to allocate another array the same size as the one we're sorting in order to do the merge sort. So I want to switch over now and look at how this algorithm works. The basic idea of merge sort is this. Sorting is difficult and expensive, so don't bother. Merging is cheaper. Cheaper to merge than to sort. The idea is based on the fact that if we partition or break up this array into smaller pieces, if we end up with an array of size 1, we can claim it's in sorted order. And then we can merge the pieces. So let's do that. We break it up recursively until we have arrays of size 1, which means we split it first in half. So we will now have 19, 2, 23, 16. And 33. 4, 27, and 1. Now we go again and we break each side up in half. Each of the sides left and right in half, and we will have 4 pieces. 19 and 2, 23 and 16, 33 and 4, 27 and 1. We go one final time, and then we have 19, 2, 23, 16, 33, 4, 27, and 1. But each of these is a partition. So we now have 8 arrays of size 1. Now we haven't actually broken the array up. What we have done is created a logical abstraction here. We have broken this up until we have 8 arrays of size 1. We haven't moved anything. We've just done this logically. So at this point we have 8 arrays of size 1, and now we merge them. So we will merge these two, these two, these two, and these two, making pieces of size 2. So here, 2, 19. Take the 2 first and then the 19. So we're not actually sorting, we're copying into an auxiliary array. And the idea behind merging is you take the smallest one first and then what remains. So here we have 16 and 23, but we're not sorting, we're merging. 4 and 33, 1 and 27. Now we go again. And once we get larger arrays, sections, it's easier to demonstrate this merge idea. So what we're going to do is join this and this together, this and this together. So we will make 2 arrays of size 4 each. So what we do is we have an index to the first element in each of these pieces that we're merging. We take the smallest one, the 2, and then we move our pointer down to the 19. The 19 or the 16, we take the 16. We move our pointer down. So now we have 19 and 23. We take the 19. And once one of the partitions is empty, then you simply take from the other side until it is empty as well. And again here, we have 4 and 1. And we take the 1 first and move down. Now we examine. We have the 4 or the 27. We take the 4 and move down. 27 or 33, we take the 27. Now this piece is empty, so we merely copy the 33. And we are done with this piece. We now have 2 arrays of size 4. So for the final step, we again merge, index here, index here. We select the smallest one, and it's the 1. Move the pointer down to the next element. So we have 2 and 4. We take the 2. And move the index down to the next element. We have 4 and 16. We take the 4. And move down to the next element. I think you can see that this is perfectly linear. You do one comparison to see which element to take. The 16 or the 27, we take the 16. And then we move the pointer down until we get to the end. So we have 19 and 27. We take the 19, move the pointer down. We have 23 and 27. We take the 23. Once a section is done, you have moved the pointer off the end, so you have finished that section. Then you just copy the remaining elements as they are into your auxiliary array. And then we have our array sorted. So this runs in big O of n log n times the breakdown and put back together steps. Here we're breaking it down to arrays of size 1. This side we start with arrays of size 1 and then we put them back together. So this is 2 log n. Now we have the merging step, and what we're merging every time is n elements. We're merging all of them. Therefore, we have n times 2 log n, and this is equal to big O of n log n. Now note that you cannot merge the two pieces into the same array. It will never work. So for instance, consider this final section with the last merge to demonstrate. We have a 1 here, and the 1 we're copying is over here. And so if we were to take that 1 and put it in the same array, we would overwrite the 2 and lose that element. So we cannot merge it into the same array. What we have to do is create a new auxiliary array of the same size and then merge into this new array. So again, this is not in place because extra storage is required, and it is storage in terms of n, the input size. It is in place because you can develop the heuristic where if you have two identical elements, you always take the first one first, which is fairly easy to do when you code. So it can easily be stable but not in place. The next algorithm we want to look at is quicksort. Quicksort is big O of n log n in the best and average cases, but big O of n squared in the worst case. This worst case is when an array is in already sorted or almost sorted order or in reverse sorted order. The algorithm is in place. It does not require any extra storage in terms of the input size n, but it is not stable. There is no guarantee that duplicate elements will remain in the same position in the final sorted array. So here we have an array we're going to use to demonstrate the quicksort algorithm. Quicksort is based on a simple idea. That is, we pick a pivot. That is, some element in this array we're trying to sort is selected as a pivot. It's important that this algorithm be efficient, so in general, the last element is picked as the pivot. So we want to rearrange the array by using swaps such that here is the pivot, and on the right hand side is everything larger than the pivot, and on the left hand side everything smaller than the pivot. So what we will do is select the pivot and then swap elements such that we have this arrangement. Now it's important to note that we are not sorting the left and right hand sides in any fashion. We are merely rearranging the elements such that this condition is satisfied, that left of the pivot is smaller, right of the pivot is larger. So I want to demonstrate how this works. We pick the 46 as the pivot. Now we set two indices at the adjacent element and then the beginning of the array. So now we're going to move down toward the middle of the array from each side, swapping as needed. That is to say, the 24 is less than our pivot, which is the 46, so it's in place. It cannot be swapped. Nothing need be done with it. So we move the index down to the 93. The 93 is larger than the 46, yet this is on the left-hand side, so it will need to be swapped. So we stop here because we've got a candidate for a swap. Now we go down to the other side and we have 89. 89 is larger than a 46, therefore it goes right of the pivot and it's already on the right side. So we're going to move down to the next element. And we have a 21. So the 21 is also a candidate for a swap. Because 21 is on the right-hand side, but it's smaller than the pivot, we want to swap it. The 93 is on the left-hand side, and it's larger than the pivot, so we swap the 93 and the 21. So we have 24, 21, 50, 82, 16, 37, 70, 93, 89, and then our pivot. Now we move down our indices to the next elements, and we check and see if a swap is needed. The 50 is on the wrong side, so it is in fact a candidate for a swap. The 70, however, is larger than the pivot, so it is not a candidate, so we move down to the next one, and it's a 37. Well, this is the right side of the pivot, and 37 is smaller than the pivot. Therefore, these two elements are on the wrong side. The 50 is on the left, but it's larger than 46. The 37 is on the right, but it's smaller than the 46, so we swap them. And we have 24, 21, 37, 82, 16, 50, 70, 93, and 89. And then, of course, our pivot, the 46, is still there. So we move down to the next spot. We have 82 and 16, so again we have the same situation. The 82 is larger than the pivot, but it's on the left-hand side. The 16 is smaller than the pivot, but it's on the right-hand side, so we swap them. We have 24, 21, 37, 16, 82, 50, 70, 93, 89, and of course we haven't been writing it, but the 46 has been here all along. It's the pivot. So now the final step in this process, because we have met in the middle here, there's nothing left to look at, we're done. This is our partition now. These are all smaller than the pivot, and these are all larger than the pivot, and the pivot goes in the middle, the 46. So in code, we simply swap the 42 and the 46. That is, the first element on the right-hand partition is swapped with the pivot. So we have 24, 21, 37, 16, 46, 50, 70, 93, 89, and 82. And here is the pivot. Notice that we don't require any extra storage to do this. We may need an occasional temporary variable in the code, but we do not need to allocate an auxiliary array the same size as the original one. That's not required. As far as stability, what I wanted you to notice is that with any algorithm, whenever you're taking and swapping elements without even looking at them, when you're just doing swaps like this, then when you're doing this, it's very easy to have a situation where you have duplicate keys, but you flip the order of them. And this is the reason why it's not stable. You're flipping or swapping elements without regard to what they actually are or what adjacent elements are. So when you're swapping elements in this way rather than adjacent ones, then you lose that stability factor. So now the algorithm is not concluded. We've done this once, but now we go left and go right and recursively do the same thing again. That is, on this side, 16 is the pivot, and we will rearrange it so that everything to the right is larger than the pivot, everything to the left is smaller than the pivot. And so I will go ahead and write this. We have the 16 here, and then we have the 21, 37, 24. The 46 didn't move. On this side, the 82 is the pivot, and so we would be swapping the 89, no, the 93, no, the 70, no. So there are no swaps here that have to be done. 50, 70, 82, 89, and 93. That is, if this is the pivot, then these are the two pieces that we have, left and right, and we swap with the element at the beginning of the right. So as you can see, now we have recursively done this. So you continue to do it on either side until you have arrays of size 1 and it is in sorted order. Now the problem that comes about with the worst case behavior is what happens if you have an array that is in sorted order. So imagine that we have 2, 4, 6, 8, 10, 12, 14, and 16. And now we want to sort this thing. So we sort it and we have 16 as the pivot. And we rearrange such that everything to the left is smaller than the pivot and everything to the right is larger than the pivot. Well, everything is smaller than the pivot, so everything's on the left-hand side. Then we take the next piece as the pivot. And so what we have is a case where the recursive calls, in the average case, if you split the array in half each time, in the average case and the best case, the splitting the array in half, that is, you pick a partition and rearrange the array, then you go left of the pivot and then right of the pivot. So you have go left, go right recursive calls on each case. And in the average and best cases, you're going to have 2 log n. So that's the best and the average case. The partitioning, you pick a pivot, then go left, go right. This is 2 log n. Then the merge step. For each of these, you have the swapping as you move down toward the middle of the partition. And so we have n log n. Let's put big O of n log n. This is the best and the average case. The worst case, however, is when we have an array that's in sorted order. Well, the best and average cases are predicated upon the idea that the left and the right-hand sides are more or less the same size. This controls the number of recursive calls that you make. And so if we have pivots of size n-1 and then the pivot, and on this side a 1, then how many recursive calls are we going to make? We're going to end up making n recursive calls. So we're going to call it with this is the pivot, the 14, the 12 is the pivot, the 10 is the pivot, the 8 is the pivot, and so on. But we're not actually going to be swapping anything. So this is going to take n recursive calls, and whether we swap or not, we still have to look at the elements in the left and right hand side, and there are n of them. So this gives us big O of n squared behavior in the worst case. Even worse, the real problem is that there is not sufficient stack space to hold this. So you begin these recursive calls, you go left, 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 and you pile stack frames onto the stack, and as you approach having piled n of them onto the stack, you then have a stack underflow and you crash. So the likelihood is high that if you attempt to sort a large algorithm that's in already sorted order with this algorithm, you will crash and the program will not succeed. It will simply crash out to the command line. So we need some kind of strategy to deal with this worst case behavior. Not only is it slow, but it will also end up crashing the program. So what are we going to do? The textbooks has several suggestions on how to deal with this problem. In essence, the problem is that every time you select a pivot, the pivot you select is the largest element in the array. Therefore, everything else is going to go left of the pivot and nothing will go to the right. But we want them to be more or less evenly distributed. So there's several strategies. One is to pick 3 elements at random and pick the median of the 3 elements. I think perhaps the most efficient strategy is simply to go to the middle of the array and swap that element with the rightmost. So that is a pre-processing step right away before you start the sort. You swap the middle element with the right-hand side, and then continue with your strategy as before. So now our pivot becomes a 10. So we end up with 2, 4, 6, 8. 10 is our pivot. And on this side, we would have, we would have 16. And this is our section that is smaller than the pivot. Then we have the larger than the pivot section. We have the 16, 12, 14, 10. We then do the swap with the pivot here, and we are left with 2, 4, 6, 8, 10, 12, 14, and 16. So this is our first step. The 10 was our pivot. And notice that now we're going to make a recursive call here. We have 3 elements on one side and 4 on the other. And this is going to give us the in log n behavior we want, because the number of recursive calls is going to be 2 log n. So finally, the quicksort algorithm is actually the fastest one in general use in terms of wall clock time. Both quicksort and merge sort are big O of n log n, but the measured time, wall clock time, is less for the quicksort. If you use quicksort, you must make sure that you fix this worst case behavior. And again, the simplest way to do this is to swap the last element and the middle element, and then go ahead and proceed with the algorithm where you always go to the right to pick the pivot. The problem with some of the strategies that are generally used in trying to optimize this is that you're adding overhead to the algorithm. That is, whatever fix-up step you're going to use to take care of this worst case behavior must be efficient. And so this simple strategy works virtually every time. The big problem is an ordered array, therefore the middle of the array is going to have the median element. So this is quick, efficient, and it does not slow down the algorithm. The next algorithm we want to look at is shell sort. The complexity is in the range, perhaps, big O of n to the 7/6 up to big O of n to the 3/2, which is big O of n to the 1.5. This algorithm is not stable, and again, it's not stable because we're going to swap elements without regard to their neighbors. And so when we do this swap, we can move duplicate elements such that they no longer are in the order they started with. It is, however, in place. Shell sort is a twist on insertion sort. Recall that insertion sort gives us big O of n behavior in the cases where the array is in already sorted order. So what we're going to do is take advantage of this fact that the behavior of insertion sort is very, very fast, very good in cases where the array is either in sorted order or in almost sorted order. So the shell sort idea is that we want to pre-process the array and get elements that are way out of the way, elements that are completely wrong, into fairly close to where they're going to end up with at the end. And the way we're going to do this is we're going to sort in bands. To demonstrate the shell sort algorithm, we have an initial array here. And the first thing we want to do is calculate an h value to get the gap between the bands. So to explain what that is, let me write the code first here. While h less than size over 3, size being the length of the array, h equals h times 3 plus 1. And then we start out with the value of h is 1. So the values for h that we're going to get are 1, 4, and then as we come through with 4, 4 times 3 is 12 plus 1 is 13. 13 times 3 plus 49 plus 1. 13 times 3 plus 1 is 40. And so on. So what these values represent is a gap. That is to say, let's look at this one. We're going to take every fourth element. So we will take 1, 1, 2, 3, 4, 1, 1, 2, 3, 4, 1, 1, 2, 3, 4. And sort these as if they were an array. What we're doing here is actually pre-processing the array and putting things in more or less sorted order. That's the big idea here. So this array has 17 elements. Size over 3 then is 5. So while h is less than 5, keep going. So we're going to stop when h is 13. So we're going to start with a gap of 13. So we will go to the 13th element. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And we note that we've only got one element, so we will fall down and reduce our h to the value that preceded it. That is, we work backwards then. Once we calculated an h value, we undo it and get smaller and smaller bands. So we would drop down then from 40 back to 13, and from 13 back to 4. So I'm going to mark every fourth element. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Now, the idea is we're going to sort this array, sort these 4 elements as if they were an array in and of themselves. So we have the 8, 26, 55, and 29, and we perform an insertion sort on these 4 elements. And when we do that, then we will have 25, 72, 16, 8, 34, 99, 17, 26, 53, 62, 87, 29, 40, 82, 14, 55, and 70. So these are the 4 elements that we have processed at this point. We have 8, then 26, then 29, then 55. So that subarray, as it were, is in sorted order. Again, notice what's happening. We're moving elements that are way out of the way into closer where they are going to finally end up. We now move down to the next. That is, the gaps move us down by 1, so every element that follows. And now we sort the 34, 53, 29, and 70 as if it were an array. To simplify, I'm just going to do this in place. So we have 34, 29, 40, and 70, and they are now in sorted order. We move down again. So we have 99, 62, 82, and this one's off the end, so there are only the 3 that we now have to do. So this is an array of size 3. We sort this array, and we have 62, 82, and 99. So here we're going to have 62, 82, and 99. '82, and finally 99. So this piece is now done. We move down to the next piece, and we sort them. So we have 14, 17, 87. And now we have finished with the gaps of 4. We have done each one of them along the way. We've done every element in this section. So now we drop down and we have gaps of size 1. And with gaps of size 1, it becomes straight insertion sort. So what you want to notice here is that even though this array is not in sorted order, it's much closer to sorted than it was when we started. So look at the end down here. We have 53, 40, 99, 87, 55, and 70. And down here we have a 72. However, most of these elements are small. So this array is in much closer to sorted order than it was when we began. So this pre-processing step gets the array in reasonably close order, so that when you're doing insertion sort and you have to insert an element, you do not have to scan all the way down the end of the array to find the place where it goes. So this pre-processing step pre-processes the array and brings it into closer to sorted order, which makes the insertion sort on the final pass super efficient. The final algorithm we want to look at is called radix sort, sometimes bucket sort. This algorithm is in big O of n in all cases. It is stable, but it is not in place. In fact, you require a great deal of extra storage for this algorithm. This algorithm has been around a long time and predates modern computers. It is suitable for use in a card sorting machine, such as were used in the first part of the 20th century. The post office has used this algorithm for sorting mail based on zip codes. So let's take a look and see how this works. So here we have an initial array to work with. With this algorithm, it only works with integers or with a character array. You can't use it on objects. The idea is we want to create buckets. This is a bucket version of radix sort. We'll discuss the radix in a moment here. But essentially what we want to do is have buckets. And so we're going to create these 0 through 9, one for each of the digits. These are my buckets. Now I want to take each number and take it and put it in the bucket based on the last digit. So 123 goes in the 3 bucket. 408 goes in the 8 bucket. 992 goes in the 2 bucket. 113 goes in the 3 bucket. 807 goes in the 7 bucket. 712 goes in the 2 bucket. 561 goes in the 1 bucket. And finally we have 332, which goes in the 2 buckets, the 2 bucket rather. So now these are dumped out into the buckets, and we're going to take them out of the buckets and put them back in our array. So we take them out in order. So we have 561, 992, 712, 332, 123, 113, 807, and 408. Notice that the array is now sorted on the final digit. We have 1, 2, 2, 2, 3, 3, 7, 8. And it turns out that we're going to do this repeatedly with each digit in turn, and when we do it that final time, the array will be sorted. So we're going to go again, but this time we're going to put things in buckets based on the next to last digit. And so, as is the case with the first pass, once we do this, the numbers will then be sorted on the last two digits. And so this is how we're sorting them. So 561 goes in the 6 bucket. 992 goes in the 9 bucket. 712 goes in the 1 bucket. 332 goes in the 3 bucket. 123 goes in the 2 bucket. 113 goes in the 1 bucket. 807 goes in the 0 bucket. And 408 goes in the 0 bucket. So now that we've dumped these into the buckets, we put them back. Notice that the dumping part of this is linear. You just scan through the array and dump it into one of the buckets. So we now take these out, and I have 807, 408, 712, 113, 123, 332, 561, 992, and so the buckets are empty and the array is again populated. Notice that the array is now sorted on the last two digits. The last two digits. 07, 08, 12, 13, 23, 32, 61, 92. So the final pass we're going to do with the most significant digits now. 807 goes in the 8 bucket. 408 goes in the 4 bucket. 712 goes in the 7 bucket. 113 goes in the 1 bucket. 123 goes in the 1 bucket. 332 goes in the 3 bucket. 561 in the 5 bucket. 992 goes in the 9 bucket. So then we take these out of the buckets, put them back in the array. And we now have 113, 123, 332, 408, 561, 712, 807, and 992, and our array is now sorted. So, this is bucket sort. We've dumped it into buckets. What we're really interested in is radix sort. Radix sort works better in the machine. Well, first of all, is there any reason to have 10 buckets? Does that make any sense? We're used to base 10. Human beings think in terms of base 10, but computers do not. Computers use binary numbers. Therefore, the numbers stored in the computer are in binary. So, for instance, suppose we have the number 100. In binary, this is as follows. Well, could we apply this bucket idea to the binary numbers? Yes, in fact, we can do precisely this. And so rather than 10 buckets, we would have 2 buckets. We have a 0 bucket and a 1 bucket. And so we do the same thing. We start out and we use the least significant bit and dump our numbers into buckets. So this, of course, would go in the 0 bucket the first time. So then we move to the next to least significant bit, and so on. So we dump these into the 0 or 1 buckets and take them out. And as we do this, first it's sorted on this bit, then it's sorted on these 2, and these 3, then these 4. And so when you get done, the entire thing is sorted, and you've only used 2 buckets rather than 10. So this is obviously more efficient. So how many steps would this take? Well, an integer in Java is 32 bits. Therefore, for each bit, you dump it into the 0 or 1 bucket, then take it out of the bucket and put it back in the array. So that would be 64n, which is equal to big O of n. This algorithm appears to be the most efficient and fastest algorithm we have. That is, it's the only algorithm we've looked at that's linear. Insertion sort is linear in the best case, which is when the array is already sorted. However, it's useless if we have an array that's not in sorted order. Not useless, but not linear either. This is linear in all cases. However, the 64n adds enough overhead that this algorithm appears to be slower than the n log n algorithms. So if you were to time radix sort versus quicksort on a computer with an array of, say, 10 million, what you're going to see is that the quicksort is faster because the 64n tends to dominate until you get to an array of sufficiently large size where it would win out, but this would take a really large array.